All righty. So a problem in plants, atmospheric pressure is such that water boils at a lower temperature than it does at sea level on Earth. If a Celsius scale is derived on this planet, will it be the same as that on Earth? Talk to me.
No, I don't think so.
Okay, they both say no. Why not?
It's a different planet. I mean,
Our calibration temperatures. What are the calibration temperatures for Celsius?
what does that mean?
The points that we use to create the Celsius.
Okay.
Remember when Anders, however you pronounce his name, Celsius originally came up with it, what did he use for his 2 calibration points?
Wasn't it like the water wherever he was or something?
No, you're thinking about Fahrenheit.
Oh, okay.
Fahrenheit used, depending on who you read, the temperature of coexistence of ice and seawater where he lived,
Oh,
and
okay.
the temperature of either his wife or a cow.
Oh, yeah. I remember that.
For his 2 calibration points, 0 and 100. Celsius used boiling water was 0 and freezing water was 100. Then he died and people flipped it over. And then in the 70s, they changed it so the calibration points we use now are 100 degrees Celsius is equal to boiling water. And 0.01 degrees Celsius is the triple point of water.
Can you explain triple point again, please?
Yeah, remember in class, we had that in our lecture, so I'm going to bring that up here.
I remember it had to do with like all 3 being at that same.
Yeah, the triple point is a single temperature and pressure. Uh-oh, got to change this here so you can see. It's totally on the recording. So the triple point is that, perfect timing, is that specific temperature and pressure, right? So the triple point of water is going to be the same anywhere in the universe because it's the only condition where that can occur. The way we do a triple point experiment is you just take a vacuum chamber, you put water in there, and you pump and you pump and you pump and you pump and you pump. And when it gets to the right point, you have all 3 of them. And like I said, I tried to do it, under teacher's guidance, never worked.
Okay.
So that is going to be the same anywhere in the universe.
Okay.
So that's one of the 2 reference points they're using for the Celsius scale. And that one's going to be same everywhere in the universe. But if you read the problem, it says that water boils at a lower temperature. So if the water boils at a lower temperature, then you're going to have a different calibration because the upper calibration point shifted, even though the lower one stays the same. So now let's look at the actual answers we have. Okay, so it will not be the same. So it's not that. Will not be the same because the Celsius scale is dependent and derived by using freezing. Well, it's not using freezing, but it's using boiling point of water. Celsius scale, derived on planet will. Okay, so the person who made this question did not take into account that the freezing point is not the calibration, but it's still going to have to be that answer.
Okay. Please.
It'll come up. Yes, this will look really good on a recording. We'll just be sitting here. It'll come up. Give it time. Okay, so you understand?
Yeah.
Nice. Okay. Next one. A physicist makes a cup of instant coffee. And of course, it's going to be caffeine free, right? Because caffeine is.
How will that be coffee? Okay.
I don't drink coffee personally, but its level drops 3 millimeters in the glass cup. Show that this decrease cannot be due to thermal contraction by calculating the decrease in level if the 350 centimeter cubed of coffee is in a 7 centimeter diameter cup and decreases in temperature from 95 to 45. So the answers here are apparently how much we're going to determine it drops.
Okay.
So let's start by making our idealized cup. Our idealized cup is a perfect cylinder, and it has a diameter of 7.00 centimeters. And so the area of the bottom is pi r squared, or pi times diameter over 2 quantity squared. Well, I'll just leave it at that for now. We can put in numbers later. And the volume, of course, is area times height, or pi diameter squared height over 4, because 2 squared is 4. So there's the equation for the volume. So we have the height of our fluid in there, the diameter marked. So we've got that laid out. Now the second part is temperature initial is 95.0 degrees Celsius. Temperature final is 45.0 degrees Celsius. And we want to explore thermal contraction because we're showing that thermal contraction does not account for this. So thermal contraction, do you remember the equation for volumetric? Let the record show the ladies are shaking their heads no. Change in volume is equal to the initial volume times beta times change in temperature.
That doesn't sound familiar at all.
We have discussed it in class.
Sorry, not at all.
So we're going to need to look up beta for water because it doesn't give us that value. So beta for water equals, and I am just going to do a
Google.
A quick Google search. Okay, so we are going between 45 and 95. So halfway between 45 and 95 is what?
95. That's 45.
70?
30.
Yeah, 70.
70.
And at 70 degrees for water, the coefficient of thermal expansion is 0.000582 per degree Celsius. So then we can calculate our change in volume. (350 centimeters cubed is the initial. 0.000582 per degree Celsius. And then the change in temperature is going to be final is 45.0 degrees Celsius minus the initial 95.0 degrees Celsius. Then we calculate. Nice, you got your calculator out.
Negative 10.185.
Negative 10.185. And what are my units?
Centimeter cube over
Centimeters.
Celsius.
Well, over Celsius times Celsius. So the Celsius is
Square.
canceled.
Oh, okay.
Okay. So
Okay,
the volume.
wait, pause.
Go ahead.
So over Celsius times Celsius?
This is over Celsius here, and then this here is times Celsius.
Why is there like? That's what I was gonna
Here.
ask.
Does that make you happier?
No. Okay, so why is there like the gap? What is it over? Or what's over the Celsius for the meter?
It's per degree Celsius. So there I put 1 over degree Celsius. Or another way I could have written this would be degrees Celsius to the -1.
Okay.
It's going to come up there. It really is. Let's move on. There we go. Okay, so what does it mean that this delta V is negative?
It's decreased.
Okay, it's decreased. That's right. The volume decreased. So the minus sign only means it decreased. Now we know volume is area times height. So the change in volume should be area times change in height, or pi diameter squared times change in height over 4. Well, I'm looking for that change in height. So let's just set the two delta volumes equal to each other. So minus 10.185 centimeters cubed is equal to pi times my diameter is 7.00 centimeters squared delta H, over 4.
The wrong one moved. Thank you.
So solving that for delta H is our last step.
Negative 0.26.
Negative how much?
0.26.
And those units are going to be centimeters because I have centimeters cubed divided by centimeters squared. How many significant digits do I have in this answer?
3.
3. We had 3 in every number.
Yeah, I didn't write it down.
So to correct significant digits, minus 0.265 centimeters. Now, the big question is, was that one of our possible answers? It is not. In fact, it's in millimeters.
Can convert. So 2.6. So do we have to convert that to mm?
Well, it'd be 2.65 millimeters if we converted it. Oh, that was the decrease. Okay, it's a glass cup. We only did half the problem. We only did half the problem. I have to be more careful. I'm actually going to erase this last portion that we did because the glass is also going to shrink.
Yeah.
Oh.
And so we have to consider that as well. So let's get rid of that. So I'm going to have volume final is equal to volume initial plus delta V is equal to 350 centimeters cubed. Was it 350 or 3? Yeah. Minus 10.185 centimeters cubed equals 339.815 centimeters cubed. So that's my V final. There's only two significant digits in this because 350 was only good to the units. And so effectively this is 350 minus 10. But we keep all of our digits until we're to the end of the problem. Okay, so that's the change in volume for water, or for coffee. Coffee is essentially water. Then we go to the cup, and the cup is made out of glass, so we need to look at the cup and say, okay, what's going to happen to the diameter?
Decrease.
Yes, it's going to decrease. And so in this case, because it's diameter, I'm going to use delta L, but delta D for diameter is equal to the original diameter times alpha for glass, delta T, right? The equation looks very similar. Delta V is V naught beta delta T. Delta L is equal to L naught alpha delta T. And then I have to look up the coefficient of thermal expansion for glass. And of course, it depends on what kind of glass you have, because there's lots of different kinds of glasses in this world. And this table here shows you all kinds of different materials. Let's just, glass, Pyrex is 4, plate glass is 9. Let's go with the plate glass, 9. And the units are times 10 to the minus 6. Nine times 10 to the minus 6 per degree Celsius again. So the diameter is going to change. Delta D is equal to my original diameter, 7.00 centimeters, times 9 times 10 to the minus 6 per degree Celsius, times, and I'm just going to put minus 50.0 degrees Celsius because 45.0 minus 95.0 is minus 50.
Mm-hmm. Mm-hmm.
Negative pi 0.
Yeah. Now that's a pretty small change.
Mm-hmm.
So now what we're going to do is we're going to calculate. So D final is equal to 7.00 centimeters minus 0.00315 centimeters equals 6.99685 centimeters.
Delta D will be negative.
Yes. Thank you.
So would this one be positive?
No, I put the negative here because I knew it was negative. Okay. So we have this for the change in diameter or for the final diameter, and this for the final volume. So now we'll calculate the heights for both cases. So the height initial is equal to the volume initial divided by the area initial, which is 350 centimeters cubed divided by pi over 4 times 7.00 centimeters squared. Let's do it. There's your pi. So there was originally 9.0946 centimeters tall. And the height final is the volume final over area final equals 339.815 centimeters cubed. Pi over 4 times 6.685.
Mm.
Equals 8.8379 centimeters. So delta H equals gives us almost exactly the same answer.
Mhm.
So there we did it as accurately as you possibly can. I am rather startled that none of those are the answer they have there. They must have used a different beta because well, let me check and make sure that calculation was right, but I'm sure it was. Yeah. So it's going to drop 2.57 millimeters. I'm not sure why it has a drop that's much smaller than that. It could be that they use if you use the coefficient for thermal volumetric expansion of water at a temperature that's like 0 degrees Celsius, well, 0 would be horrible. If you use like the value at 10 degrees Celsius, it's much, much smaller. 20 degrees Celsius is less than half of this value, which would still give you an answer bigger than what they have. I think they must have just used a different coefficient for expansion. But we did use the most reasonable number to use, the value it has in that ballpark. It actually ranges from, at 9 degrees Celsius, it's 0.000695 per degree Celsius. And at 50, it's 0.000457. So it's changing with temperature.
Okay.
I am perplexed by their answer, but.
So what did they actually have?
Well, the one that they considered correct, they considered the 0.8321 correct. We could actually back out what they used for beta
To figure out, yeah.
to figure it out, because so that's about 1/4 of what we got. And so that means they used betas about 1/4 of what we have, which would be somewhere around 0.0015 or something like that.
Mm.
Which is like the coefficient of expansion at 15 degrees Celsius.
Okay.
A little disconcerting that they have a different number, but if they gave us a coefficient of thermal expansion to use, then we could have, gotten the same answer.
Okay.
Okay, did you want to do more?
Yes, please.
Okay, let's see.
Oh, it's like the subject of this is almost weird. Why does it work?
Was it?
Oh, so on the equation sheet.
Mm-hmm.
So would this one be just the protonal?
Those are the same equation.
Oh, length. Okay.
All right, on to the next one, which may or may not show up here in just a moment. You can see, there it is. Suppose a gas-filled incandescent light bulb. Incandescent light bulb means you have a wire that gives off light because it's hot. So the light bulbs we have here are not incandescents. So that the gas inside the bulb is at atmospheric pressure when the bulb temperature is 20 degrees Celsius. Find the gauge pressure inside such a bulb when it is hot, assuming its average temperature is 60 degrees Celsius, an approximation, and neglect any change in volume due to thermal expansion. So what's our concept going to be here?
Looking to gauge pressure using temperature and volume, changing volume.
Well, the volume is going to be constant because we're
neglecting. Sorry.
Yeah, neglecting any change in volume. We're going to make the approximation that air is that the gas inside is an ideal gas. Without knowing what the gas is, it's really not a fair assumption, but it's probably accurate. So we're going to assume an ideal gas. So what's the equation that relates temperature and pressure and volume for an ideal gas? Yeah, PV equals nRT, the ideal gas law. So in that equation, P is the pressure, V is the volume, N is the number of moles of gas. Well, it's sealed, so that can't change. So the V is fixed, N is fixed, R is a constant. So pressure is equal to NR over V, which is held constant. So I put parentheses around the constant, multiplied by temperature. What unit do I need to use for temperature here?
It says Celsius is what they're being used, but if we're doing a change, wouldn't it be Kelvin?
If it's a change, it doesn't matter, but this is not a change. This equation does not have change in temperature. We're going to go through a temperature change, but the equation is not based on temperature change.
Okay.
And so I'm going to have to do pressure 1 over pressure 2. Well, let's do it the other way. Pressure 2 over pressure 1. pressure 2 over pressure 1. I know what pressure 1 is. Pressure 1 is 1 atmosphere. Is nR over V times temperature 2 over nR over V times temperature 1. And you see, aha, the nR over V's, the nR over V's are going to cancel. And so pressure 2 over pressure 1 is temperature 2 over temperature 1, but I have to use kelvins. So temperature 1 was 20 degrees Celsius, or 293.15 kelvins. And temperature 2 is 60 degrees Celsius, so that's going to be 333.15 kelvins, if I did my math right. So pressure 2 is equal to pressure 1. T2 over T1 is equal to 1 atmosphere, because it just says 1 atmosphere somewhere here at atmospheric pressure. Pressure 1. Uh-oh. Stopped riding there for a sec. I was like, I told you I was having no problems. So 1.14. Actually, we have 5 significant digits on our temperatures. And so, assuming it's exactly 1 atmosphere, which is kind of a bold assumption, we'd have 1.1364 atmospheres. So that's the pressure. Find the gauge pressure. What does gauge pressure mean? Gauge pressure is the pressure minus a reference pressure, which is almost always atmospheric pressure. So it's going to be pressure 2 minus pressure atmosphere, or 1.1364 atmospheres minus 1 atmosphere equals 0.136 atmospheres.
Wait, so gauge pressure is a pressure minus atmospheric pressure?
It's almost always atmospheric. Gauge pressure, is, at least as I understand it, is the pressure minus a gauge. A gauge is a reference.
Right.
And so almost always that reference is
It's
atmosphere.
going to be atmosphere. Okay.
For this one, how do you know that P1 is 1 atmosphere?
Right.
Because it said right here.
Okay.
Oh, so whenever it says at atmospheric pressure, it's just assumed that it's 1 atmosphere.
Yeah, atmospheric pressure means 1 atmosphere, yeah.
Okay.
And there's no significant digits implied there. So for all we know, this could have, 1 significant digit or 7.
Okay. Gauge pressure is a pressure minus the reference pressure. Okay. Would we have to draw anything for that type of, if we were to have that?
There's virtually nothing to draw because you just draw a bulb.
Right.
Okay.
So I was kind of lazy on drawing pictures. I drew a picture for this one, but this one here, well, there's no pictures to draw on it.
For the test, the one that about the blood flow, are we supposed to draw?
Oh yeah,
The one for
the one with the capillaries. I couldn't
Yeah.
figure out how to do that.
You should have had your capillaries coming together into a vena.
Nope.
And so you have...
I think I got the answer, but I did not draw a picture.
Nothing.
Okay.
Okay, so the next question. The actual final pressure for the light bulb will be less than calculated in part 1 because the glass bulb will expand. What will the actual final pressure be taking this into account? Is this a negligible difference? So the glass bulb, let us assume it's a sphere. Well, actually, we can... There's nothing here to talk about the volume. There's nothing here that talks about the volume of the gas-filled light bulb. But we can calculate delta V is equal to V naught beta for glass, delta T. So delta V over V naught, that is the percent change in volume, is equal to beta for the glass, delta T. Yeah, it's fine. I could have done it the other way. It would have been just as good. So what is beta for glass? Well, we looked up here alpha for glass, right?
Mm-hmm.
And alpha for glass was 9 times 10 to the minus 6 per degree Celsius. Beta is essentially 3 times alpha. So we're just going to put beta for glass.
But it wasn't the same glass that they had.
It doesn't say what kind of glass this is. It's the volumetric coefficient for volumetric thermal expansion for water that we had significantly different than they must have used.
Okay.
3 times 9 is 27.
Mm-hmm.
So we'll use 27 times 10 to the minus 6 for beta for glass. So delta V over V naught is equal to 27 times 10 to the minus 6 per degree Celsius times the change in temperature, which is 60 degrees Celsius minus 40 degrees Celsius, or minus 20 degrees Celsius. 4 times 27 is...
But it has to be.
Yeah, they're the same.
Okay.
Okay, so that's how much the volume is going to change. It's going to change by 0.1%. I think we can already say that's going to be negligible, a 0.1% change. But if we wanted to be really, really careful, we would say P2V2 over P1V1. Well, actually, no, let's do like we did before. P2 over P1 is equal to NR over V2, T2 over NR over V1, T1. And now we can only cancel the NRs.
For this one, there is no unit.
There's no unit, that's correct. So this is going to be the same numbers that we had before. So I'm just going to put 1.1364 for the T2 over T1 because we already did that. And then my V1 over V2 is going to be 1 over 1.00108. Right, because the volume increased by this amount that we just calculated. And so if I take I'm going to come back up here to get the full number. And divide that by 1.00108, I get P2 over P1 equals 1.1352. Therefore, P2 is equal to 1.1352 atmospheres, and P gauge is equal to 0.1352 atmospheres. And now our question is, did that make any difference? Well, we dropped from 0.136 to 0.135, but that's a pretty insignificant change.
Okay. So for V2 here, you do 1 plus...
1 plus the delta V, yeah.
Okay.
Right, because all I know is V1 equals unknown, V2 is equal to V1 plus delta V. But then because I had the ratio, V1 over V2 is equal to V1 over V1 plus delta V. So that's what I...
Wait, so is that the pressure gauge is equal to that?
That's the gauge pressure, not the pressure gauge. Yeah. Right, because the absolute pressure is the 1.1352 atmospheres. Now, the next ones are from material that was on the last test in this assignment. So I'm guessing you don't want to go over that stuff at this point?
No.
So do you want to go on to the next?
Sure. Please.
Please. Of course.
Mm-hmm. Because the one is what our atmospheric pressure was. So subtracting that is what the gauge actually would be.
Okay. Suppose that the average velocity, the RMS, of carbon dioxide molecules, it's sinking now, and it gives us the mass of a molecule. Well, it says molecular mass is equal to 44 grams per mole. That's the molar mass, as liquid habit. We physicists apparently aren't very good at this. In a flame is found to be 1.05 times 10 to the 5th meters per second. What temperature does this represent? Comes from today's lecture.
Yes, I see RMS. I remember that.
I see RMS, and I know today's lecture certainly had RMS in it. Okay, why is this thing still not updated here? It says sinking. They both say sinking, so, what could go wrong?
Drown.
Yeah, I was thinking the same thing, but...
Where is it? I see nothing about RMS. Thermodynamics.
There we go. So what was the relationship between RMS speed and temperature?
Oh, okay. So RMS speed is the speed of a gas molecule that has the average kinetic energy. And then we were talking about how kinetic energy is the temperature of is it the molecules or
Well, the temperature tells us about the average kinetic energy of the molecules.
The temperature tells us. So the kinetic energy doesn't tell. Wouldn't the kinetic energy do the same?
Yes. Yes.
Okay.
So here we're looking for temperature. So we want the equation that relates temperature
Yeah, I don't have
with
that.
the RMS speed. And it is, well, this is solved for VRMS, so we're just going to put it that way. We have VRMS is equal to the square root of 3 times Boltzmann's constant times temperature over the mass of a molecule, which is the same as 3 times the molar mass constant over the molar mass.
One real quick, it shouldn't take long.
What's that?
They need your signature. I wanted to get it from Barry Forbes, but they said I can just get it from you. And also,
Just to add the AS.
and also to put like a signature right here.
Now,
Because
your major is still staying business, though, right?
yes, it's still business. I'm just
So-
adding biomedical science.
Biomedical
to it.
science as,
Yes.
as a minor, or no, as a major as well.
Yes.
Well, yeah, the AS. Make sure you note somewhere on here that you want to keep your old advisor.
Yes,
Right,
I already spoke to her. She
Okay.
actually put this down for me, so she knows. Yeah.
Okay, just want to make sure that we don't end up with, oh no, now all I have is web,
Yeah.
and I don't have my
Yeah,
major
she still has
advisor.
it. And also, she put you can be able to approve my classes and stuff.
Once that's turned in.
No, you already can
Oh, I can.
because you're my so
Pre-professional.
pre medical is like
Mhm.
my declaration.
Oh,
So
okay.
because you're underneath it, you can approve it. And I already put it in. So please, if you can approve it.
Okay.
Thank you.
Was today the first day of registering?
So yeah. Oops.
Which reminds me, yeah, graduation thing.
I've been working on it, honestly. It's just I've been having trouble pulling stuff together. Yeah.
Well, we can talk about it.
Okay.
Okay, but not while we're recording.
No.
So, which one of these two versions do I want to use here?
Average kinetic.
We know him.
Which M do we know?
Small.
No, we know the big one.
Big one.
We know the molar mass. It says molecular mass, but they gave us clearly the molar mass.
Yeah.
Grams per mole is molar.
Okay.
Okay, so we're going to use this one here. So I need to solve that for temperature. So I'll square both sides. The RMS squared is equal to 3RT over M. So what's T equal to?
Wait, I'm sorry, what?
So
Oh.
I took the underlined parts and squared them.
V squared times M.
Yeah,
Divided by 3.
divided by 3R.
So we just put in our numbers. Would you consider 10 to the 5th meters per second fast or slow?
Very slow.
Very fast is the correct answer.
Uh-huh.
Okay, now that's in grams. Grams is not our SI unit. I need to convert that to kilograms. And what is R? funny. I don't have this memorized. I know the Boltzmann constant, but I don't know R.
Sorry.
8.314 joules per mole Kelvin. One, two, three, 4, 5, 6, 7. They have 1.95. You know why theirs is different from mine? I probably should have kept one more digit on R.
Oh.
Because we have 1.9449. Obviously, that rounds down to 1.94.
Mm.
But if it'd been even a smidge higher, it would have rounded up to 1.95. Okay. Any questions there?
Not at the moment. I don't know. It's still fresh, so it's still like new information, so it's like complete confusion to me anyways.
Okay, the next problem. What's the average kinetic energy in joules of hydrogen atoms on the 5,500 degrees Celsius surface of the sun?
Wasn't the other one, didn't it have kinetic in it?
Right there. Kinetic energy average.
Oh,
No.
hello.
So all I have to do is just put in numbers. This is real tough. 3/2. Boltzmann constant is, there must be a second page of the equation or something. Yeah, okay. So yeah, there's more equations here. So there's K. See, there's R. If we would have kept one more digit of R, see, it was 3144598. It would have definitely gone up to the value they had. So 1.38065. Obviously, don't need that many digits. Times 10 to the 23rd joules per Kelvin. Times temperature. What's the temperature on the sun's surface? What do I put in my equation?
Oh, we're doing in Kelvin.
It's negative 23rd, right?
Yeah, minus. I forgot the minus sign. Okay. So we got to use kelvins.
Oh, 273.15.
Yeah.
5.
I didn't put the 0.15. Oh, that's, I can't read. That's not a 6, that's a 9. Or I skipped 9. It's 1.20 then times 10 to the minus 19. Yeah, I don't know what picture I could have drawn for this one.
Yeah.
Either.
I don't know how to draw anyway, so it's just a struggle.
Well, you've seen my artistic skills. I'm not.
So the concept is kinetic energy.
Average.
It's the kinetic theory of gases.
Oh.
Kinetic theory of gases.
Right, both of these, that was basically the concept. The next one is exactly the same, except for it's helium atoms in the corona.
So it would be just
And
plugging it in.
It would just be plugging in exactly into the same equation. And the fact that one is hydrogen and one is helium doesn't matter for the kinetic energy, because we don't need the mass for the kinetic energy. It was for the speed that we needed the mass. So let's skip past that one.
Okay.
So the next one, similar to the one we've already done. Oops. So this time, let's see you guys take this one over.
Whoops.
What do you mean?
Temperature changes the same energy constraint. So we'd have to go back to like
The delta L.
yeah. So this one. So we have the change in temp. We have the initial length. We just need the alpha thingy.
Yeah.
Okay. So Mercury has a coefficient of linear expansion of 61 times 10 to the minus 6 per degree Celsius.
And we have to change.
Kelvin.
Don't we have to change it to Kelvin?
No.
It's a temperature change,
Yeah, I always.
so you don't have to.
Okay.
You still can.
Too much work. So what does the alpha stand for again?
Alpha is the coefficient of linear expansion.
Coefficient of linear expansion. Okay. So alpha for
So it is 3. Oh, they have to note too.
3 centimeters.
Okay. 61. 10.
Oh, meters.
3 Celsius.
Oh, it doesn't matter that it's in centimeters. Why does it matter that it's not in Celsius? I mean, that it's not in meters?
My answer is going to be in centimeters, and so I'm going to have to convert my answer.
Oh.
So I have
Okay.
5.49 times 10 to the minus 4 centimeters, or 5.49 times 10 to the minus 6 meters. Oddly enough, they have 5.4 times 10 to the minus 6 instead of, well, it does round down to 5.4 now. No, rounds up to 5.5. So, you guys nailed that one. Huzzah! Yay! Go team! Okay. Next. Because you know I'll do this, well, not all day, but until it's time for me to go home. It's either this or grade, right?
Okay, yeah. I could see why.
All right, calculate the number of moles in a 2-liter volume of air in the lungs of the average person. Note the air is at 37.0 degrees Celsius body temperature.
Calculate the moles.
So in.
Turn the page. Oh, no. Yeah. Nope. Nope. Yep.
Why
Ideal
again?
gas law.
Okay, you said why?
Ideal
did.
gas.
Oh, you did. Okay. So, why are we going to use the ideal gas law?
Because there's gas in our lungs and we're dealing with air.
Okay. Because like I told you in class, the air at room temperature behaves very much like an ideal gas. So for ideal gas, PV equals nRT, where N is the number of moles. We're asked to find the number of moles, so we just solve that.
Do we know?
What's the pressure in our lungs?
Is it 1 atmosphere?
Yeah, it's 1 atmosphere. So 1 atmosphere, there are lots of different variations on R, with different units. So I'm just going to put for now 1 atmosphere, and then we can change it later. The volume is 2.00 liters. The temperature, what's the temperature?
37. The Kelvin.
Oh, 273.15. 310.15?
And then the
I could have
R.
done that in my head. Whoops.
Yeah. Then the R. So we have atmospheres, liters, kelvins. So if we look up the ideal gas not ideal gas constant, but the gas constant. And we will find various units. I'm just going to go to Wikipedia. I'm sure it will give me different units. Values of R. I'm just looking down here in the units, and liters, atmospheres, kelvins, moles is 0.082057. So I can have more ability to write accurately. 0.082057 liters times atmospheres per Kelvin times mole.
Why?
Why what?
Liters times atmosphere. So that cancels that. Oh, and then it gives it moles.
I use those, so it gives us the answer in moles. And NICE has 0.0786 moles. Yeah. Okay, and then the rest of these are... Okay, there's one more that's not... Nope, I take that back. The rest of these are all stuff that was covered on the previous. So that's all the new stuff. I've got to put up more SHWs for you.
Yeah.
Okay, anything you want to go over here? Or are you good?
We'll just have to go over it.